Okay, we're going to get through it all. We're going to make it together. If we work together, we can accomplish anything. So the first, let's see, what do we have left? We have, so this week's lab is this week's lab is just the post-test of that intuition measurement device. It doesn't count for your grade, but it's helpful for me to sort of, figure out what kind of stuff is working in lab, what kind of stuff isn't. And for taking that test, I'll give you 1 point back on an exam. On one of the 5 exams, the big exams. 1 point back. That's a lot. That's a good reward. That's true. That's undeniable. I can't deny that that's true. And then the only thing we have left after that is the final, exam 5. And I think I've written this now in notes several times, but exam 5 is Monday, 12/12 at 6 p.m. in S1326. Or, if it works better for you and you can make time during the day, you can take it on Thursday instead. Give yourself a few extra days to study. 12:15. The time is 2 p.m. It's the room next door, 1328. So you don't have to tell me ahead of time. Just come to whichever one works.
Are they the same as the other exams, 24 points?
Yeah, they're always the same number of points. It's different questions, but they're meant to be equivalent, yeah. Anybody have any questions about the end of the semester? Yes?
Is the test, I know all tests are about everything, but is this test going to be
focus more on old stuff? Probably not, because we have a lot of new material on it, But yeah, the idea is you should be ready for anything, my plan is to cover the new stuff that we need to, and then sort of at random pick old stuff to put on it. So your goal is to be ready for any of the questions related to any of the practice problems we've had. That's the idea. Yes?
So you would pick random problems from the practice problems opposed to the lecture, the exam, old exam problems?
Well, I think I would sort of look at practice problems, and yeah, I think my exam questions are always pretty similar to the practice problems. So that's what I do. Like, I'll look through the practice problems and say I'm going to do one like this one, and then I'll change a couple things. But yeah, the practice problems are still the way to go. You can think of the exam questions as just extra practice problems if you're tired of working on the same ones, The same with the in-class examples. They're all kind of getting at the same material. But the test questions won't be any new format, sticking stuff together that hasn't been stuck together yet or anything like that. Any other questions? Okay. Well, there are 2 sets of practice problems that we still haven't gotten to, but one, if you look at them, is super short. And both of these are really they fit together as kind of one topic. This topic is rotational motion. And it's broken up into rotational kinematics, that's just describing the motion, talking about things that you could figure out from a videotape. And rotational kinetics, and rotational kinetics is kinematics plus the causes of the motion. So up until now, everything that we've done has been particles. We've only used particles so far. And particles have two properties that are important for mathematically how we treat them. So particles, and these two things are related. The first one is we assume everything happens at a point. So there's no difference between a force acting on one part of a body or a force acting on another part of the body. We're just treating the body like it's all in one spot. And then the second thing, related, is with particles, we don't care about orientation. We can't make any distinction because everything's in one location. And so if you don't care about the orientation of an object, often particle approach is what you want to use. But, you know, there's a lot of cases where it's critically important what the orientation of the object is. And so in that case, we have to use rotational kinematics and rotational kinetics in addition to particle stuff. Now, both of these matter. We have to know where on the body forces are applied, and we have to know what way the object is facing. Rotational motion is not circular motion. But they're very closely connected. So let me give you a demonstration. This is circular motion. Okay, I'm moving in a circle. But my orientation, I don't know, who knows what my orientation is, but the key part is my feet are moving in a circle. Okay? Rotational motion is this. It doesn't matter where my feet are going. all that matters is my orientation is changing. Okay? So they're different. But I'll show you why they're related. Rotational motion is the change in orientation. Circular motion is just that particle, whatever point you're tracking, is moving in a circle. So here's why. Here's why they're connected. Say that you have a board that's free to rotate on a hinge, you know. So say that this is a board like nailed to the wall, and you can take it and spin it around, and the spot that'll stay in place is that nail or bolt or whatever it is. So this is a board rotating around a fixed bolt. This thing is changing orientation, but think about what individual material points on this board are going to do as it spins around. This point here is going to follow that circular path. This point here is going to follow a different circular path. So when an object rotates, the individual material points move in circles around the axis of rotation. So that's why the circular motion equations are going to pop up, you know, in and out and throughout this topic, is because these individual points on any rigid body are moving in a circular path. So if I'm in rotational motion, you know, like my fingertips doing a circle. You know, the gills are alive. Okay, one thing that's going to make all this easier to remember how it all fits together, especially, but also maybe intuitively a little easier to understand what's going on, is there is a close relationship between all the equations and quantities that we used in translational motion, in particle motion, and the new quantities and equations we're going to use in rotational motion. So these are the rotational and translational analogies. So I'm going to set up this two-column table. Translation refers to the stuff that we've been doing up until now. Translation just means moving around where we're not, we don't care about the orientation. And then the other column is rotation. So for translation, we have the position vector. In rotation, we have, it's the Greek letter theta, and I'll call that angular position. That one isn't going to come up too much, but You can think of that as a description of what orientation the body is in. The next one is velocity. And so with translation, you have a velocity vector. With rotation, you have what's called angular velocity. It's the Greek letter omega. That's a lowercase omega. And the definition of omega has the same relationship to angular position that velocity does to position. I'll go through all that, like all the derivations of all this stuff looks the same. The next one for translation is acceleration vector. And for rotation, we have an angular acceleration. It's the Greek letter alpha, lowercase alpha. And these are the quantities that make up kinematics. And then after we're done with kinematics, with translational motion, we define mass. And with rotational motion, we have something sort of like mass too. It's capital I sub A, and it's referred to as the mass moment of inertia. After we defined mass in translational kinetics, we defined force vector. And in rotational motion, analogous to that is something called the moment of a force about a point. Sometimes it's referred to as a torque. So like a torque wrench is a measurement of that moment. And finally, the thing that we're working up to is after we defined all these things, we introduced our major equation of motion. The most important equation in this class is Newton's second law, and it says the force vector is equal to the mass times the acceleration vector. And exactly analogous to that is the rotational version of Newton's second law that you actually can derive from Newton's second law, and it says add up all the, that's not a very good M, add up all the moments about the axis of rotation. That's equal to the mass moment of inertia times the angular acceleration. So it has the analogous quantities in the exact same places as Newton's second law. So in a way, you don't have to remember any new stuff. All of the, we're going to have to learn how to interpret this rotational stuff, but all the equations are going to look the same with the new quantities in place of the old quantities, and it's going to follow this form so much that, you know, if you sort of store these in the same part of your brain, you get two things for the price of one. You know what I mean? Okay, so I'm going to just go down this list and we're going to define these things. The first one is angular position. The units for angular position it's an angle, and this is the first time in this class that we've had to use angles in radians. You don't have to change your calculators to radians, though, because the only reason that you need to switch from radians to degrees and back in your calculator is for the trigonometric functions, and we're not ever going to need to use radians in cosine and sine, but we are going to have to represent all this stuff in radians, but you can keep your calculators the same. One thing that's different between the translational position and the rotational or the angular position is the angular position, unlike the position vector, holds for the an entire rigid body. And so the way to think of angular position is choose a reference vector on the body. You can think of that as painting an arrow on the body. The angular position is the counterclockwise angle from the arrow's original position, or its original orientation, to its new orientation. Okay, so here's an example. If the body you're tracking is a car, and you paint a vector on it like this at the original orientation. Bless you. And then after you go through your unsuccessful YouTube video, your new orientation, you know that paint stays on the car, so I guess it would look something like that, right? Then here's your original orientation. Here's your new orientation. And this angle here is the angular position. So in this case, that'd be like, say, 120 degrees or something. We're used to dealing with it in degrees, but to represent it in radians, so to convert from degrees to radians. You can use the fact that pi radians is equal to 180 degrees. So say that this angle is let's say that's 110 degrees. So to convert, 180 degrees is equal to pi radians. The degrees cancel, and you get 110 times pi over 180. Can someone tell me what that is? I'm going to wait here all night. What? 1.92. Okay. 1.92 radians. 1 radian is about 60 degrees. Any questions about that? And so just like with the other angles that we've used, you could represent this as a positive angle going counterclockwise or a negative angle going clockwise. What did I say? Positive going counterclockwise, negative going clockwise. One thing to notice, did I already say this? When a body rotates, every point on the body has a different position vector. But the entire body is represented by one angular position. And that same thing is going to hold with angular velocity and angular acceleration too. So same with angular velocity and angular acceleration. Okay, so on this picture, let me just show you what that means. Okay, so say you have a coordinate system in the middle here somewhere. This point over here is in the positive x direction. You know, you would have a positive x component of a position vector. This point back here would have a negative x component. They have different position vectors. But this whole body is represented by the orientation of that arrow you painted on it. And so the angular position holds for every one of those points. It's just there's one angular position for the whole car. Anybody have any questions yet about angular position definition. Okay, so next is angular velocity. And this is going to be defined in terms of angular position, the same way we did that with translational velocity. So remember, with translational stuff, we defined the average velocity as equal to the position at some later instant minus the position at some earlier instant divided by the elapsed time. And then what we really wanted the whole time was to define instantaneous velocity, not the average velocity. And you can think of that as the instantaneous velocity is equal to, or is approximated by the position at the later instant minus the position at the earlier instant divided by the elapsed time for the instants t1 and t2 really close together. We talked about it in terms of that pinching thing where little by little we brought those two times closer together and we converged on a instantaneous velocity. So now with angular velocity, we can define an average angular velocity as a later angular position minus an earlier angular position divided by the elapsed time. We don't really care about that, though. We really care about instantaneous angular velocity. And so we'll think of that as being the average velocity for two instants that are just really close together again. So the instantaneous angular velocity is theta 2 minus theta 1 divided by the elapsed time for time 1 and time 2 close together. The units for angular velocity are radians over time. And so SI units are radians per second. And there are two things to notice about angular velocity. The first one is, well, it's angular velocity, is a measure of how quickly an object's orientation is changing. And second, if an object, well, let's say a positive angular velocity means the object is rotating counterclockwise. And a negative angular velocity means the object is rotating clockwise. Any questions about that? And then the last thing we have to define for rotational kinematics is angular acceleration. So remember, for translational kinematics, we define the acceleration vector as the velocity at some later instant minus the velocity at some earlier instant divided by the elapsed time. We didn't make a distinction between average and instantaneous acceleration because when we were doing this stuff, we were only dealing with constant acceleration, so it was all the same. And this idea, this definition of acceleration is the same thing we're going to use to define angular acceleration. So now, the angular acceleration is equal to the angular velocity at a later instant minus the angular velocity at an earlier instant divided by the elapsed time. The units for angular acceleration are radians over time squared. And so the SI units have to be radians per second squared. And there's one important relationship between the signs of angular velocity and angular acceleration. Who can predict what I'm going to say? Yep. So, yes, same as the other one. If angular velocity and angular acceleration have the same sign, the speed of rotation is increasing, you know, it's speeding up. So if omega and alpha have the same sign, the rotation is speeding up. And if omega and alpha have opposite signs, the rotation is slowing down. Now, there are two more sets of equations that we're going to use a lot. The first one relates translational quantities to rotational quantities. So these are equations to go back and forth between translational and rotational quantities. So the first one says that the magnitude of the velocity, or the speed, I'll write it like this, is equal to the absolute value of the angular velocity times r, where r is the distance from the axis of rotation to the desired point. I'll do a couple examples after I give the second equation. And then the second one says the magnitude of the tangential acceleration is equal to the absolute value of the angular acceleration times r. R means the same thing here. Okay, so here's an example. Am I going too fast? Too slow? Yeah. All right, so let's say that there's a board, and it's rotating about this pivot point. And it's rotating counterclockwise with an angular speed, you know, the absolute value of angular velocity of 10 radians per second. And slowing down at 5 radians per second squared. So let's say that there is a point on the object that we're interested in for some reason. You know, it could be an engineering application or whatever. Could be an engineering application. Let's say this distance is 0.3 meters. And we want to know, first, I'll call this point P. What's the velocity vector at P? And second, what's the acceleration vector at P? So this is one of those ones where we're going to have to use what we know about circular motion and the equations that I just gave. So first of all, let's think about what the path is of this point P. This pivot point is fixed, and so that point P is just traveling in a circular path like that. And I think I didn't write it down, but I said that it's moving counterclockwise. So it's moving this way. So the first thing we can do is figure out the speed from the equation. So we'll use that the speed is equal to absolute value of omega times r so v is equal to 10 times what's r? The distance from the pivot point to the point that we care about. That's the point 3. And so you get 3 meters per second. It's sort of a funny thing with the unit of radians. Radians are, a lot of times we write down radians because it's sort of easier to visualize what you're talking about, but radians are really a pure number. And so what we have here is units of radians per second, or really, since radians is just a number, that's 1 over seconds times units of meters, and so we get meters per second. And now we have to think about the direction. We have the speed. Well, the object's moving in a circular path like this. It's moving counterclockwise, so the velocity is this way. And so the velocity vector is 3 meters per second down, or in our usual coordinate system, that's 0, -3 meters per second. Any questions about that? Okay, so now we need to figure out the acceleration vector. The acceleration of that point, the acceleration of the point at P comes from the circular motion. So the acceleration is the sum of the centripetal acceleration and the tangential acceleration. So the acceleration is a centripetal plus a tangential. The equation that I just gave gives us the magnitude of the tangential acceleration, and that's equal to the absolute value of the angular acceleration, 5 radians per second squared, times r, which is 0.3 again. And so you get 1.5 meters per second squared. Okay, so let's think about this motion. It's moving this direction. We already figured out its velocity vector is this way. Is it speeding up or slowing down? And so the tangential acceleration has to be that way. The centripetal acceleration is towards the center. Okay, the centripetal acceleration is the speed squared divided by the radius in this direction. That's what did I say the speed was? 3. So in part A, we calculated the speed as 3 meters per second. So 3 squared divided by the radius of 0.3 in this direction. So that's 30 meters per second squared. Any questions about that one? And then the tangential acceleration, we just figured out the magnitude of it is 1.5 meters per second squared. And up here we figured out that it was pointing up. That's in the positive y direction, so this is 0, 1.5 meters per second squared. And so the total acceleration is 30, 0 plus 0, 1.5, so 30, 1.5. And so if there was something, sitting on, if there was a bug on this board and you're trying to figure out how fast you have to spin it to get the bug to come off, if you know the bug's mass, you can do all the physics, figure out the, the coefficient of friction, you could do all the physics to figure out how fast you'd have to spin it before the friction couldn't provide that acceleration anymore, just with Newton's second law, the way that we've done these kind of problems up until now. Any questions about that example? So here are the last 3 equations for rotational kinematics. And they're the rotational versions of those constant acceleration equations that we use forever near the beginning. So the first one says angular velocity final is equal to angular velocity initial plus angular acceleration times time final. You know, all of these equations are going to be exactly analogous to the translational constant acceleration equations. This is like the VF equals VI plus ATF equation. And then theta F is equal to theta I plus omega I TF plus 1/2 alpha TF squared. And then the last one says 2 times alpha times the quantity theta F minus theta I is equal to omega F squared minus omega I squared. Has anyone here ever worked with a centrifuge? Yeah. How big are they, the one you work with? That's, okay. We'll say a meter across. Okay. We'll say a meter across. I've never seen one, but. So let's say that there's a centrifuge. That accelerates from rest How fast does it take to get to its top speed?
Not very long.
10 seconds? Less? Okay. We'll say 2 seconds.
5.
I just want you to be happy.
Go 5.
Okay, 5 seconds. A centrifuge accelerates from rest to what's a good speed? A good angular velocity? RPMs? How many RPMs? 2,000 RPMs? Okay, so 2,000 RPM. So 2,000 RPMs in 5 seconds. If the radius of the centrifuge is 0.2 meters, what's the acceleration of whatever's in their blood cells, of blood at 5 seconds? Okay, right at that instant when it reaches that top speed. We're doing important medical research right now, cutting edge research. What's the acceleration? Okay, so 2,000 RPMs. So rotations per minute. One rotation is one time around. So that's 2 pi. So 2,000. So rotations per minute. One rotation is 2 pi radians. And then 1 minute is 60 seconds. Can someone calculate this out? So this is, the rotations will cancel, the minutes will cancel, and we'll end up with an angular velocity in radians per second. It's like around 200. 209.44 radians per second. Okay, well, to come up with the acceleration of particles out at the outer edge of the centrifuge, we're going from rotational stuff to translational stuff. So we know that we're going to have to use these equations. You know, we're going to have to use these two equations relating translational to rotational. So we're going to need that angular acceleration. Okay, so we want the angular acceleration. So we can use this equation. Omega final is equal to omega initial plus alpha times time final. Our final angular velocity is 209.44. Our initial, it's at rest, so that's 0. Plus alpha times time final is 5 seconds. So alpha is equal to, what's that, 42? 41.89. That's radians per second squared. Okay, so now what we need to do is, I didn't specify anything about the direction of rotation or anything like that, so we can choose our own. I guess I'll choose counterclockwise. And let's think about a particle over here at the edge. This acceleration is going to be biggest at the edge. That's why I chose it. The acceleration, actually, we would find for particles that are near that are right at the middle, the acceleration would be 0. But okay, so the velocity is this way. Is it speeding up or slowing down? Speeding up, so the tangential acceleration is also that way. The centripetal acceleration is this way. And now we have to use those equations that go between translational and rotational to come up with magnitudes for these things. The speed is equal to the angular velocity at that instant, 209.44, times the radius, which I think I said was 0.2. So that's, what, 41, what is that, 41.88? Oh, we already did that. Okay, that's meters per second. The magnitude of the tangential acceleration is the angular acceleration times that radius. So 41.89 times the radius of 0.2. What do you get for that? 8.38 meters per second squared. Okay, so the centripetal acceleration is the speed squared divided by the radius. So 41.88 squared divided by 0.2, moving in the negative x direction. What do you get for that? 8769, I'll just leave it like that, meters per second squared, or negative 8769, 0 for y. The tangential acceleration isn't much compared to that, but that's in the positive y direction. So 8.38 up, or in components that's 0, positive 8.38. And so the total acceleration is negative 8769, positive 8.38 meters per second squared. Or a total acceleration of about like 1,000 Gs. Which is, super, super high, and that's why it's capable of separating things with different masses. You can see that the way we set the problem up, almost the entire acceleration comes from centripetal acceleration. It comes from the speed that it's going, rather than how quickly it's spinning up, I think we learned a lot about centrifuges today. Anyone have any questions about this example? Yes?
So omega times the distance from the axis of rotation is the same as alpha?
Say that. What?
So why?
Oh, yeah, that was just a weird thing with the radius, I think.
Really confused.
That was because that just had to do with the numbers I chose. It was because to get the angular acceleration, we divided by 5, and then to get which is the same thing as multiplying by 0.2, which was the radius.
Okay.
So that was a freak accident. Any other questions about that? All right. Well, that's angular kinematics. So next time we'll talk about angular kinetics. There's only like 3 angular kinematic problems, so you should be able to do all those now. So take a look at those as soon as you can.